Let's take a beam of sunlight, that is white light, and send it through a prism. It spreads out into a rainbow. What our eyes perceive as a rainbow, a continuum of color, is actually a wavelength scale, going from about 0.4 microns at the blue end to 0.7 at the red end. That's a factor of 1.75 from one end to the other. A factor of 1.75 isn't very much. Compare it to, say, music, where a factor of 2 in wavelength is called an octave. So visible light spans about an octave. The 88 notes of a piano, a sort of auditory rainbow, spans more than 7 octaves. It makes you wonder what our eyes might be missing. Here's an image of the biggest neighboring galaxy, Andromeda, at visible wavelengths. Most of the light we're seeing comes from stars. This is what it would look like if we could see infrared radiation. The data in this image comes from the Spitzer Space Telescope. Most of this infrared radiation, which is colored red in the image so we can see it, is from warm dust that's embedded in the otherwise invisible hydrogen gas that exists throughout the spiral arms of the galaxy. And this image emphasizes the ultraviolet range, based on data from a different space telescope called GALEX. The ultraviolet rays are coming mainly from young, hot, massive stars that are strewn throughout the spiral arms. Without the help of detectors that are sensitive to ultraviolet and infrared, our eyes would miss out on these interesting details. And that's just the beginning. Let's zoom out for a broader look at the electromagnetic spectrum. Now our scale spans 16 orders of magnitude. That's roughly the range over which we've detected photons from celestial sources. It's equivalent to 53 octaves, or more than 7 piano keyboards. Naturally, we'd better use a logarithmic scale to see what's going on. The wavelength scale ranges from 100 meters down to 10 to the minus 14 meters. The frequencies in hertz go from 10 to the 6 to 10 to the 22. And energies in electron volts go from 10 to the minus 10 up to 10 to the 8. Different parts of the spectrum go by different names: radio, millimeter, microwave, far infrared, near infrared, visible, ultraviolet, EUV, X-rays, gamma rays, and so on. As I've said before, it's important to remember these are artificial boundaries. Nature makes no sharp distinctions, and humans do because we use different technologies for focusing and detecting photons of different energies. For our purposes, we only need to divide the spectrum into 3 parts. We're going to lump together the infrared, visible, and ultraviolet and just call it optical for short. Everything with lower energies, longer wavelengths, we'll call radio. And everything to the other side, with higher energies and shorter wavelengths, we'll call X-rays. Those are the 3 main cultures in observational astronomy: optical, radio, and X-ray. The astronomers use different technologies, different units, and different jargon. They often have a hard time talking to each other. For example, radio astronomers often label electromagnetic waves according to frequency, megahertz or gigahertz. Optical astronomers tend to use wavelength, nanometers or microns. And X-ray astronomers prefer energy, kilo-electron volts. I'll say more about the origin of these cultural divides later in this lecture. For now, let's return to the topic of why we build telescopes. Among the reasons we discussed last time was to detect invisible radiation, to go beyond the visible range and explore all those other orders of magnitude. I also made an analogy between a telescope and a bucket for collecting rain. It's a nice analogy, but it fails in one major respect. A bucket collects rain no matter what direction it's coming from, whether it's falling vertically or coming in at a slant. For a telescope, that would be bad. We would have no idea where the photons are coming from. We want to point the telescope at something, a star or a galaxy, and only collect the photons coming from a narrow range of directions. We want to make an image in which each pixel of the image corresponds to a different point on the sky. Mathematically, an image is a mapping between the direction the photons are coming from and the position on some surface, whether it's a pixel in a CCD camera or a cell in your retina. Ideally, we want the number of photons that hits each point in the surface to be proportional to the rate of photons arriving at the Earth from a certain direction in space. But we haven't said how a telescope performs that mathematical mapping. How does it sort the photons by incoming direction? Conceptually, the simplest way to make an image is with a pinhole camera. Think of a completely dark room except for a small hole in one wall admitting light, and there's a screen on the opposite wall. The light that hits a given spot on the screen must have come from the specific direction defined by the line from the hole to that spot, which means there's a one-to-one correspondence between the x-y coordinates on the screen and the direction from which the light entered the hole. At least there would be a one-to-one correspondence if diffraction didn't exist. Photons coming from angles differing by less than about lambda over d radians get blurred together in the image because of the diffraction of electromagnetic waves. Let's think about how we can achieve the tightest possible focus. Say the distance from the hole to the screen is f, the so-called focal length, and the hole has a diameter of d. We'll start with a big hole and imagine the light from a distant star goes straight through the hole. Ideally, we want the image of the star to be a pinpoint on the screen, but because the hole is so big, the image is actually a luminous circle of diameter d. To shrink the circle down into a pinpoint, we should reduce the diameter of the hole. But at some point, d becomes so small, the diffraction limit starts to dominate, and the image of the hole stops being a crisp circle and starts fuzzing out. If we keep reducing d beyond that point, the image gets worse because the diffraction limit goes as lambda over d. The optimal case, the tightest focus, is when the angular diameter of the circular image, d over f, is equal to the diffraction limit, which is roughly lambda over d. Solving for d, we find that it's the square root of lambda times f. So we've just learned that the ideal size for the pinhole is on the order of the geometric mean of the focal length and the wavelength. If f is, say, a meter and lambda is a micron, then d should be of order the square root of 10 to the minus 6. That is 10 to the minus 3 meters, which is a millimeter. So that's a pinhole camera. Simple and effective. No lens or mirror needed. But there's one big drawback. That optimal hole is so small, hardly any light gets through. So while we can make sharp images over a wide field of view, the images are faint with a very low signal-to-noise ratio. Even a daylight scene might require an exposure lasting minutes or hours. That makes pinhole cameras totally useless for optical astronomy, where the light levels are down by so many orders of magnitude. But variations on the pinhole camera do find use in astronomy, when we have no other choice. Very high energy photons, X-rays and gamma rays, punch straight through most materials, so we can't easily build mirrors or lenses to redirect their trajectories and focus them. But what we can do is drill a pinhole in a layer of a dense material like lead or tungsten that's thick enough to block them. And then for the screen, we can use germanium crystals or other materials that produce an optical flash when a high-energy photon hits it. To mitigate the problem of the small hole, astronomers drill several widely spaced holes. This makes the pattern on the screen confusing because now it's the overlap from lots of different pinholes. But if you observe the same scene multiple times with the camera in different orientations, there are computer algorithms that can disentangle the information and reconstruct the scene. That's called a multiple pinhole camera. There's another variation called a coded aperture telescope, which has been used by X-ray astronomers. There's also a better but more expensive solution to the X-ray focusing problem that I'll describe later. In the optical and the radio domains, photons don't pack as much energy, so we can use mirrors to focus them. This allows us to collect much more light than a pinhole camera. At optical wavelengths, you could use a lens instead of a mirror, but lenses have a problem. Because they're made of glass, they act like prisms even when you don't want them to. The amount that they deflect the light depends at least slightly on its wavelength. That introduces chromatic aberration. What should be a white point in the image turns into a multicolored blob. That's one reason why astronomers use reflective optics, glass mirrors coated with aluminum or silver. Another reason is that a big mirror is easier to support than a lens. Only one side of the mirror matters, the reflective side, so you can lay it shiny side up on a stable supporting structure, as opposed to a lens, which you can only grip on the rim or else you'll block the light. Now, let's talk about what kind of mirror we want. It has to be curved to focus the light. One possibility is to use a mirror whose surface has the shape of a parabola. What's special about the parabola is that all the photons coming in along the symmetry axis get bounced to the same point, the focal point. So a parabolic bucket not only collects them, but also redirects and concentrates them into a small area. And that's where we can put a detector. I am so tempted to show you the proof that the parabola has this focusing property, but in the interest of time, I'll leave that for your own enjoyment. One way to do it is with calculus. Starting from the equation of a parabola, y equals x squared over 4f, where f is the focal length, you apply the law of reflection. It's fun. But back to telescopes. Parabolic dishes are used in radio telescopes. You point it straight at a source of radio waves and measure the radio static coming from that direction. And to make an image, you can slew the dish through a range of directions, recording the intensity of the static as you go. At shorter wavelengths, it's more common to use the imaging property of the parabola in addition to the focusing property. Photons arriving head-on, straight down the symmetry axis of the parabola, all end up at the focal point. But what about the ones coming from a slightly different angle, off-axis? They don't get directed to the focal point, but they do get concentrated near a different point, displaced to the side from the focal point. For small angles, the displacement is proportional to the incoming angle, which is just what we want to make an image. It's a mapping between the incident direction and the location in a surface. To capture the image, we insert a two-dimensional detector with lots of separate pixels, each of which can record the intensity at a point in the focal plane. For optical astronomers, the detector of choice is the charge-coupled device, or CCD, which uses a thin layer of pure silicon. Photons hit the silicon and knock loose some electrons, which can then be trapped and counted by electronics that are mounted on the silicon surface. Interestingly, optical astronomers rarely use parabolas. You see, it'd be wonderful if all the photons from a given direction get sent to a single point in the focal plane. But that's not the case. Only the on-axis light is focused perfectly. Off-axis, the rays hitting different parts of the parabola land in slightly different locations in the focal plane. That causes image distortions, or aberrations. Stars near the middle of the image appear pretty sharp, But away from the center, they look like little cones or comets. That's why this type of distortion is called coma. Maybe we should search for a better shape than the parabola, one that would focus light to a single point no matter which way it's coming from. Nope, there's no such shape for a mirror, even in principle, that lacks aberrations. James Clerk Maxwell and Ernst Abbe proved that in 1856. Instead, what astronomers do to reduce aberrations is to use multiple mirrors. The light hits a primary mirror and bounces to a secondary mirror, which is also curved, before going to the detector. Having more than one surface that you can adjust gives the optical designer the freedom to reduce whatever kind of aberration is worrying you the most. You can use mirrors with elliptical or hyperbolic cross-sections instead of parabolas. You can even use 3 mirrors. Now, let's return to the electromagnetic spectrum and recount a little history. Until the 19th century, all astronomy was confined to the optical band. Just after 1900, William Herschel discovered infrared radiation, and Johann Ritter discovered ultraviolet. Then, in the 1860s, James Clerk Maxwell revealed light to be an example of electromagnetic waves, which could have any wavelength in principle, and it became clear that there were unexplored orders of magnitude on either side of the optical band. So naturally, astronomers raced to build machines to detect radio and X-ray photons and see what celestial wonders they would reveal. Actually, no, that's not at all what happened. The truth is, very few astronomers anticipated radio astronomy or X-ray astronomy. The sun's spectrum peaks in the optical range, as do the spectra of other stars, if you include infrared and ultraviolet. And what else is there besides stars? Many astronomers thought that those far-flung regions of the electromagnetic spectrum were probably dark wastelands. One way to see their point is to ask, what would be the temperature of an object whose spectrum peaks at a given wavelength? For that, we use Wien's law. The wavelength at the peak of the Planck spectrum is about 1/5 of hc over kT. Solving for t gives hc over 5k times lambda peak. In the optical range, the temperatures are on the order of 5,000 Kelvin, and that's where we find stars. The sun's outer layers are at 5,800 Kelvin. The reddest, coolest stars are a few thousand Kelvin, and the bluest, hottest stars are around 30,000 Kelvin. So to produce X-rays with a photon energy of 1,000 electron volts, you'd need a temperature of 2 million degrees Kelvin. That once seemed crazy. What would be that hot? And at the other extreme, for the peak to be in the radio range at, say, a gigahertz, the temperature would be about 0.01 Kelvin, which seems equally crazy. At such low temperatures, the total flux, which is proportional to t to the 4th, would be pathetically low, so you wouldn't be able to detect something so cold. Now, everybody knew at the time there's more to life than just the Planck spectrum. The sun, for example, emits strong non-thermal radio waves due to magnetic activity at its surface. But even so, the sun is a very feeble radio source. If there were a twin of the sun 10 parsecs away, we'd barely be able to detect it at 1 gigahertz, even with a modern radio telescope. That's why radio astronomy didn't originate with astronomers. It grew out of electrical engineering. Karl Jansky, a radio engineer at the Bell Telephone Laboratories, was the first person to detect the radio static coming from astronomical sources in 1931. And for nearly a decade after that, the world's leading radio astronomer, essentially the only radio astronomer, was Grote Reber, an engineer who built his own backyard radio telescope as a hobby. He had a grand old time mapping all the brightest radio sources in the sky. He was the first person to see the radio constellations, so to speak. What distinguishes radio astronomy from the other types is that the wavelengths are long. This has three important implications. First, it's easier to build a focusing mirror. As a rule of thumb, the mirror needs to be polished with an accuracy of at least 1/10 of a wavelength. That is, it needs to conform to the shape of a parabola or whatever surface was chosen to within λ/10. That is a whole lot easier when lambda is a meter than when it's a millionth of a meter. And that's why Grote-Reber could make a 9-meter radio dish as a hobby, whereas an optical telescope that big costs tens of millions of dollars and takes years to build. That's also why the world's largest telescopes are radio telescopes. The big dish at Arecibo in Puerto Rico is 305 meters across. And in 2016, China completed the construction of a dish 500 meters across. The second implication of the long wavelengths of radio waves is that their wave nature is much more conspicuous than their particle nature. In fact, nobody ever calls them radio photons. We always say radio waves. And we can use purely wave-based methods to detect, amplify, and to combine radio waves. It's not really like counting photons. It's more like following the rise and fall of ocean waves, which means that our earlier discussion about Poisson noise doesn't apply in radio astronomy. The statistics are different. And it also allows for the possibility of interferometry, an amazing trick to improve our angular resolution. You'd think that radio images would have terrible angular resolution because of the diffraction limit, which goes like λ/d, and lambda is 1,000,000 times bigger than in the optical range. But in fact, it's the radio astronomers who enjoy the best angular resolution of all. How can that be? It's because you can combine the waves from two widely separated receivers. Say we have two dishes at a distance b apart. B is for baseline. And there's a radio source straight overhead, sending down waves, a pattern of crests and troughs. Both dishes detect the waves and amplify them without losing track of the phase, and then send the signals to a central computer called a correlator. The correlator merges the two signals, which would combine constructively in this case, since the crests from the straight overhead hit the dishes at the same time. Crest plus crest, you get a big signal at the output. Now imagine the source is not straight overhead. The waves are coming in at some small angle, delta theta. Now the crests will hit one of the dishes first, then the other. In the small angle approximation, the extra distance the wave has to travel to hit the second dish is b times delta theta. Well, if that's equal to half a wavelength, then the waves will interfere destructively when they're combined. Crest plus trough gives 0 signal at the output. So the output of the correlator can tell us whether the source is straight overhead or if it's displaced by an angle of λ/2b. So we can resolve details in the radio image on that angular scale. It looks just like the diffraction limit, except remember, b is not the diameter of a single dish, it's the separation between the dishes. We can put them kilometers apart if we want and achieve the same angular resolution as an enormously large telescope. Now, a problem might have occurred to you. What if we increase theta some more so that b delta theta is now an entire wavelength? At that point, we go back to constructive interference. That means with only the output of the correlator, we can't tell whether a source is directly overhead or if it's at an angle of λ/b from the vertical, or 2 λ/b, or 3 λ/b. They all lead to constructive interference. That sounds very confusing. We can get around this problem by building more than two dishes. Each pair of dishes is sensitive to angles that form a fringe pattern on the sky, with the fringes perpendicular to the line between the dishes. If the correlator is getting information from lots of different pairs of telescopes with baselines in different directions, then those crisscrossing fringe patterns allow you to pinpoint the source to a specific location on the sky, so you can make a proper image. The Very Large Array, or VLA, in New Mexico is an interferometer with 27 radio dishes. They can be moved along railroad tracks to spread them apart as much as 36 kilometers, so it can achieve the same angular resolution as a 36-kilometer radio dish. The catch is, it doesn't have the sensitivity of such a big dish. The VLA can't collect nearly as much radiation as that bigger dish would, but at least it solves the angular resolution problem. There are even networks of dishes that are separated by thousands of kilometers spread across the Earth. I alluded to one such network in an earlier lecture, the Event Horizon Telescope. That's how we hope to resolve the details of what's happening in the vicinity of the black hole in the center of our galaxy. Let me give you an example of the wonders that radio telescopes can reveal. Here is an optical image of a galaxy in the constellation Hercules. The galaxy appears to be a blob of starlight at the center of the image. Now let's overlay an image from the VLA at radio wavelengths, which we'll color red. Wow! There are jets of intense radio waves shooting out in opposite directions, and then they billow out into giant clouds many kiloparsecs away from the galaxy itself. What is going on here? What's happening is there's a vortex of gas surrounding a giant black hole in the center of that galaxy. The gas is getting swallowed up and disappearing into the black hole, but some of the gravitational potential energy that's released when the gas falls from far away ends up getting thrown outward in both directions at nearly the speed of light. It's probably a consequence of the rapid spin of the black hole. These jets might be aligned with the rotation axis of the black hole. The jets consist of streams of charged particles that are whirling in circles because of a strong magnetic field that threads through the jet. And remember, when charged particles accelerate, they radiate. In this case, a lot of the radiation comes out at radio wavelengths. Let's swing over to the other side of the spectrum, to the X-rays. The first thing to know about X-ray astronomy is that the Earth's atmosphere is totally opaque to X-rays. X-ray photons are energetic enough to knock apart molecules and rip off electrons. So what happens is they slam into a molecule and they get stopped. They never make it to the ground. Now that's great news for life on Earth. It keeps us from getting fried. But it's bad news for X-ray astronomy. That field couldn't get started until the 1960s, when advances in the space program made it possible to put telescopes above the atmosphere. You would think astronomers would have learned a lesson from the episode of Karl Jansky and Grote Reber. You'd think they would have jumped at the chance to explore the X-ray domain. But no, a similar story can be told. Traditional astronomers were not clamoring to launch an X-ray telescope. The pioneers were from high-energy particle and cosmic ray physics. Two of those pioneers were Bruno Rossi and Riccardo Giacconi. They convinced NASA to launch an X-ray telescope in 1962, even though many astronomers were skeptical that there would be anything to see. And of course, the sky turned out to have a glittering display of X-ray sources, which are now understood to be related to black holes, neutron stars, supernovae, all kinds of fascinating phenomena. I already mentioned the difficulty of focusing X-rays. You can't just use a regular mirror. The photons would penetrate through it instead of getting reflected. We talked about one solution, the coded aperture mask, but there is another. It turns out X-rays will reflect from metals as long as they strike the surface at a very grazing angle, like skipping a stone off the surface of a pond. X-ray mirrors looked like polished metal cylinders, but they're not exactly cylinders. The sides are slightly sloped so that X-rays can skip off the surface and land on a CCD for detection. It's a serious challenge, though, to polish the surface of an X-ray mirror to an accuracy of λ/10 when lambda is just a few nanometers. That means it needs to be smooth at the atomic scale. But if you want sharp X-ray images, you got to figure out how to do it. In 1999, NASA launched the Chandra X-ray Observatory, which makes the sharpest X-ray images of any facility. The Chandra mirrors are glass coated with iridium, and to boost the collecting area, Chandra uses multiple mirrors, nesting small ones inside the larger ones. And there's a second set of hyperboloid mirrors to reduce the image aberrations. It's very clever and very expensive. The time to research, develop, and implement that mirror technology took more than 20 years, and the mission cost billions of dollars. Let's wrap up this lecture by looking at one of my favorite X-ray images. Here's an optical image of a star field in the constellation of Cassiopeia. There doesn't appear to be anything unusual, just a bunch of stars. Now let's overlay a Chandra X-ray image. That is, we'll superimpose a false color image in which red and blue correspond to X-rays of low energy and high energy. There's a gorgeous glowing X-ray source with a flower-like texture inside of a bluish haze. What we're looking at is the aftermath of a supernova explosion. It's called Tycho's supernova remnant. A massive star exploded here. The light reached Earth about 500 years ago, and the surrounding gas is still extraordinarily hot, X-ray hot, millions of degrees Kelvin. With our optical blinders on, we'd completely miss out on this amazing drama and so many other invisible, unexpected wonders of the universe.